Okay, so we talked about Morse theory yesterday, as you can see. And we did it classical. Morse. Then we did it discrete. Or combinatorial more properly. And this is something that Forman did. And then I basically introduced an earlier version. So historically speaking, this should have been here. And I think also logically speaking, because it's much more intuitive, PL1, and this is Banchoff. Okay. So, and then we discussed some comparisons, and perhaps I'll go back to those comparisons and I'll pick up from there, okay? Sorry, I should have done this just before we started, but, and yes, and there was another thing, if you remember, this guy here. So we use all this stuff to do persistent homology and persistent homology, we suggested, yes. And we should remember that Forman also did. Okay, so Forman also did Ricci curvature. And we saw that it's very natural to take it into account and do also persistent homology using this thing. Yes. So that's what we know after yesterday's talk. Yes, it works. Thanks.
Is it okay? Yeah, well, for the presentation.
Then I'll switch off. Okay, so that's how we stand for now. And then, so there are connections, yes? So there is a natural development, or rather an unnatural development, because you should have done this before this in practice. But once you use Forman, you remember it has a Ricci curvature, so you can use it also for persistent homology. And that's more or less what we learned yesterday up to, oh, sorry, I still have to go more downstairs, yes. Okay, so we got to this thing, if there is a connection between the two, between the approaches, between Forman and Banchoff, and that's when we got to Bloch. And we saw that there is a connection indeed, which says that you can pass through one type of discrete Morse theory to the other one just by taking the subdivision, and instead of having critical cells in Forman taste, you'll have them critical vertices in Banchoff approach, or Banchoff flavor. Okay, and then we saw that they are not quite the same. So in one sense, you pass the dual, so there is a natural way of going back and forth. And actually, it's a good thing to do this simplicial subdivision, because if you want to represent something in R3 or Rn in general, it's much easier to think of simplicial complexes. So simplicial complexes, polyhedral complexes in general, are much more easier objects to understand than hypernetworks or whatever. And then we ask ourselves if the two theories are equivalent or at least as strong. And we saw that at least apparently, Bloch, it's true, they are the same. But we saw, especially so since by this result of Benedettian and the parasito, the Forman discrete Morse theory is stronger than the classical one in bounding the homology of the manifold. And I forgot the rule that Thomas recalled, but I did have a proof, small one. At least I did that. There is no sign of, sorry, there is no sign for, Helmholtz symbol, but there was no place for it anymore. Okay. So I'm happy I did that. And indeed, in dimension 7, classical Morse theory and discrete Forman Morse theory are equivalent, yes? So this is an amazing fact, given the situation that, or given the observation that it's very hard to really comprehend what Forman methods prescribes. It's easy to implement it, though, for a computational viewpoint. And dimension 7 should suffice twice over, yes? Nobody does anything more than triangles as sometimes tetrahedra. Yes, we discussed this not just once during our school. And it was not me who pointed it out first. And we saw that they are not quite the same, nevertheless, because they capture different things. So yes, you can pass from one to another. You can apply each of them for basic tasks, but Forman goes to the homotopy type to do the kill, and Banchoff, as we saw, goes through curvature, basically discrete curvature, and thus Euler characteristic, therefore is much more homology and geometry flavored. Okay. So we saw there are a lot of advantages and disadvantages. One of them being that Forman works for unweighted objects. And so when you wanted to apply it in, let's say, as we did for networks, you have to artificially weigh your networks to be able to do persistent homology. Okay. And we saw that you really need a barycentric subdivision. I went the other way around. Oh, yes. I'm sorry. Okay. Okay, so now that's where I stopped yesterday, I think, yes? So I said that Banchoff's Morse theory holds only for PL manifolds or more general convex cell complexes. So you can't really apply the equivalence between the two Morse theories except in this setting. And there is a way of doing it, however, to extend Banchoff's Forman Morse theory in more general cases, in spirit similar to Banchoff, but for more general class of spaces. And this is what is called Bloch's stratified Morse theory. So I won't get into it at all for now. I thought about it, but it's rather technical. I'll finish my basic program, and then I say a few words about other possibilities, because it's really, really very technical. So if anyone wants to know more, after what I'll tell in 5 or 10 more minutes, then they can look at this paper. Okay, so this is one problem. The other problem with the two approaches is Banchoff's Morse theory. It's not really usable in higher dimension. So there are at least two ways of getting out of this problem, this quandary. One is to go back here at what I wrote, and to see that I mentioned the name of Forman. Forman does Ricci curvature as well. well, it's time to remember and to go back to it. Okay, so that's the trick. You can use the Forman-Ricci curvature to do persistent homology. And the idea is as follows. It's very simple. I'll just go over the moves. Again, I'll show you where you can find more information. And in the end, I'll add something about this ping pong between categories and techniques through discrete curvature. So remember that if I'm working on a combinatorial network or a combinatorial graph, I take into account only the number of edges, adjacent edges and adjacent triangles. So adjacent edges is just a degree. If you remember, it was that 4 minus degree of one vertex and the other one. And now since I plumb in the triangles, we just talk about triangles for now, I have to delete 3 times the number of triangles. Here, absolute value denotes the number. So once you have a vertex, we saw you can define the scalar curvature at this vertex. It's just a Ricci curvature of the incoming edges divided by the degree, yes? So we saw that earlier. So if I have a vertex, V, and edges E1, E2, E3, let's say, then of course the degree, the Ricci, the scalar curvature, scalar Forman curvature at V is the sum, is Ricci Forman of VI from 1 to 3 divided by the degree by 3, yes, so on and so forth. So this is very simple. And then doing a bit of combinatorics, you can write this version when scalar curvature of scalar Forman curvatures at a vertex is nothing but 2 minus the degree of V minus the mean curvature. Or in other, so remembering what combinatorial curvature means, i.e. the number of triangles, we get this expression. So we have a connection between degree, combinatorics, the scalar Forman curvature, or simply put Forman curvature, and the combinatorial curvature of a vertex. But so when I see combinatorial curvature, what do I think of automatically by now, or I should think? Banchoff, of course, Banchoff Morse theory. So here I can do by now classical Forman Morse. Here I have Banchoff, so this is a connection, and it kind of works very nice because we have the following. This basically proves the result. So here the proof goes first the proof, or idea of the proof, and only then the statement which says that if you have we have a Forman-Ricci curvature-based persistence scheme for hypernetworks. And this is what resides. If you remember, I started this all this discussion from a simple observation that my friends did experiments with persistent homology using Forman's Morse theory, and they did it using Forman curvature. And they got very, very similar results, and they couldn't understand why. The answer is very simple, just because of this fact, because they are connected. If you do this kind of persistent homology or this kind of persistent homology, we basically do get the same thing up to some combinatorial counting. So in fact, what it means that these two things are equivalent, and you can apply them whatever you prefer in what is easier for you and what your tastes are. So you can find more details in here if you really want. If you don't, you don't. Okay, and so this should have been everything, all the Morse theory in one row, and perhaps, okay, so let me finish and then go back, okay? So had it gone fluently yesterday everything, then I would have gone to this last slide, saying that after all this Morse theory, I am a little hoarse. I should have been spoken for 2 hours, speaking for 2 hours in a row. So it should have been a decent pun. I'm sorry. That's how you distribute talks. Then even bad joke is becoming even worse. So it's time to say again thanks and to ask about questions. Now, what I want to say is, I know you want to get rid of me, but I'm looking at the clock, so I'll add a bit more, okay? So this is our original plan. I planned for 6 classes, and in the end there were 7. So as I said, this kind of Procrustean things. Please don't cut off my legs, yes. Sorry?
No, try not to cut your legs.
No, thank you so much. This might help. So please see that questions are each time different. Personally, okay, I liked the old Kühnel and Hamangia culture, the small guy in the beginning. So now I said 2 more things which I would like to add. One is that I promised some people, including you, I think. Sorry, I don't recall your name, but I remember faces and questions. Is that I thought there are more ways of doing persistent Morse theory, thus potentially persistent homology. Some of them better and some of them less good, some of them ideally mathematically ideal, but perhaps not good practically, and the other way around. You never know. So as I said, Bloch's approach, which generalizes Banchoff, takes the basic idea is the index is 0 at critical point, 0 at regular points and non-zero at critical points. Yes. So what he does, he establishes a connection between discrete Morse functions and piecewise linear functions. So he starts with a generic discrete Morse function on a combinatorial manifold, and then he constructs a Morse function, a generic one, corresponding to it, which is linear on the cells, which are just a barycentric subdivision of M. So he passes from generic Morse function to piecewise linear Morse function, also generic, and this allows him to do all these things. And then he says that each vertex in M has an index which is the index with respect to F hat in the sense of Banchoff, because now I have a PL thing. So it passes through discrete one to Banchoff, but in a more controlled manner. It produces the right functions rather than just the subdivision. And then non-critical cells have index 0. And what's very nice and useful is that critical cells in dimension k has an index of -1 to the k. So it's very easy to compute Euler characteristic and Morse inequalities. Yes, plus minus and so on and so forth. It's very nice. So what kind of objects are included in? So you'll have things that are not manifolds. So things that look like this. You can have these kind of trees structures or what might be called books. Yes. So they are non-manifolds because a point here has no neighborhood is homeomorphic to a disk, but they're still kind of decent. So they are stratified. Actually, is a quite, I'm sorry to say, but it's not, except of Banchoff and Morse, of course, again. And of course, Morse, nobody writes very charming in the field. I mean, it's hard work to read. Of course, the more complicated things get, the more difficult reading is. Yes, so if you want to make writing and therefore reading. Okay, so there are more pastes or more everyone likes his own taste of, or his own flavor of Morse theory. So there is some of these guys here, Grunert, Kühnel and Rote, made a serious advance, so to say, I mean, I think, in along the Banchoff Morse theory. So they strengthened it. It's rather new. I got an email from one of them, those that says, oh, well, we have this new thing. It's somehow better. You should use it. And I'm really looking forward. I still didn't have the chance to try it. It's stronger, therefore it's harder to use. Yes, we should understand by now. Yes, the simple thing is to use the Pythagorean theorem. To do Riemannian matrix needs a bit of schooling. Yes, and so on and so forth. Finsler manifolds even more. I mean, there is a quid pro quo here. Yeah, and I'm sorry. So if somebody thinks he's in game for it, please go and do it. Yes, I strongly recommend it. So it has some advantages because Banchoff is hard to use in dimension higher than 3. I mean, don't get me wrong. You have the same formulas, the same intuition, but it's harder to see 7-dimensional manifolds. And I say 7 for 2 reasons. One, because 7 is the biggest small number, and because all the real pathologies, in my opinion at least, and the pathologies start in the famous pathologies in topology start in dimension 7. You have this spheres that are the same, basically topological, but not diffeomorphic, as you say. And something else, which is a big improvement, I wasn't even aware, I have to confess, but that Euler characteristic is not rightly seen also or computed in for certain types of critical points. So that's an improvement that these authors made. And for some pathological objects, one of them is called the Beer sphere. Thomas is here. Yes, it's beer. Beer. I feel like a beer sphere. I'm game. So it's stronger somewhat. Method is based on homology and not on homotopy. So this is their paper, which appeared not long ago, yes? Okay, so that's their approach. This new approach is the same in dimension 2. And the same, when I say the same, it's like classical Morse, like high school stuff. In dimension 3, which, by the way, by now we know that dimensions 2 and 3, it's all we can hope to do really in practice. It's like in dimension 2. But you also have a new type of critical points, which are of mixed types. It depends, so to say, which direction you look at them. So it can be of index 1 in one direction, index 2 in the other one, which is kind of, and with arbitrary multiplicity. So it's a big improvement. And I should say that apart from this paper, there is a PhD thesis which goes in much more details, of course, and it also gives exhaustive literature in detail. So that answers your question. But I'll say something about this myself. There are other approaches, and there are some of them which when I started preparing my talks, you won't believe it, but I started from this because Roberto wrote me, perhaps you'll do something like that. I was, okay. So I started reading, and it was kind of cool. I mean, as a mathematician, that's what I liked. So there is an homotopy approach suggested by Bestvina, Mladen Bestvina, This is the name that I told you yesterday, Mladen Bestvina. And I know him, I think I met him once or twice, but more importantly, I know his work, yes? So he has this paper with Braude and another one in mathematical communications. You see, this is for sure a strong paper. This is easy to read, I would say. And everyone brings to the game his strengths and inclinations and talents, yes? So Bestvina, of course, brought very nice applications to geometric group theory, okay, graphs and TITS buildings and stuff like that, which are very geometric algebraic objects, so to say. And since, if I may say so myself, if Cayley graphs are attackable in this manner, of course, any graph could be explored in this manner. So that's my hint, okay? And also they worked on configuration spaces and on braid groups. There is an application, somewhat different approach, but basically the same idea of Farley and Sabalka on for braid groups. So when I was a PhD student, that happened at some point in time. By now, things got distant, or not things got, I don't know, depends on how I feel. We had a lot of people who were doing that because one of the two topologies or three topologies at the Technion was deep in this, had a big result, and John Bierman was coming a lot and visiting. So of course, he talked a lot about braid groups. I don't know how modern they are anymore, yes, things, but it's always good to go back to the basic things. I really don't get out of this. But I think they are relevant, yes? You know, it's not passé or something. Okay, so this is what my education being somewhere, of course, it's topology, but with a strong layer of algebra, although you can't see it is here. I'm always charmed about this. Yeah? I worked on Klein groups. Anyhow, so there are other approaches. One, the most general, and it also seems the earliest. That's what you try to mention to me, Nicholas, yesterday. So the earliest approach is purely topological. It's based on charts. There are some works of Kosinski and Wilson Kuiper and Grunert as well, the same Grunert we saw earlier. It works in dimensions smaller than 4. That should do the trick. It's very general. It should be adaptable. I have to confess, I didn't have enough time to really, get deep into it. I felt it's less easier to apply perhaps in practice than Bestvina's. Bestvina seems ready-made for that. So sometimes you have a lot of depth, but it's not fitted for certain application. And of course, that doesn't make mathematicians stop and they try anything just because they like the mathematics, yes? But it's not always good applications, I should say. Good applications, you need mathematical knowledge and understanding, and also some common sense, what works and where, yes? There are a lot of papers that say, oh, this is very applied. And in fact, it's just a beautiful theoretical paper. And the other way around, I know a lot of papers, especially in graphics and imaging, there's a lot of tensors and stuff. And in the end, it's just brute force computation using something else. So questions. I said there are more. I have different signs for everything. This is something which, just a second. This is something which Roberto didn't like, I thought, so it's the last, but I put more, more cultural questions. Okay, so that's it, I guess. I don't know. Yes, of course. You saw some. You weren't here yesterday, but there are applications. Let me see if I have something. No, I don't have anything more here. But in Forman's, so Forman's approach has this advantage. It has some disadvantage as well. Nobody's perfect, yes? So I'm sorry, I whoosh back. So his approach is based, it's combinatorial, but he produces vector fields, combinatorial vector fields. When you have combinatorial vector fields, you can do dynamics. And that's why they use it, for instance, for the visualization of, sorry, such objects as, so here they use it, for instance, they produces vector fields to visualize the flow on a tour, on a blind bottle and stuff like that. Yes. So you should Forman Morse theory dynamics, and I'm sure 12 papers that it will appear. If not 12,000, I don't know. So there is, of course. But it depends on what you want to do. There was something else which I wanted to say. Yes. I mean, I can stop right now, but then I'll feel somehow that I'm cheating of some time. So what I wanted to show you is something, okay. So you saw in what I proposed, I showed that these approaches are essentially the same, so you can, via passing to Banchoff, you can show that the Forman Morse and Forman Ricci approaches are equivalent, are the same. Because in the end, it's a bit of combinatorics, but it's not just counting edges, you have to plumb in the faces and to do polyhedral geometry. That's what I was, if you remember when I started my talks, I said that the right thing to do, the right context is not graphs, but rather simplicial or polyhedral complexes, because they capture modeling and they give you enough geometry to do something intelligent, to use apparatus which is not forced. And so again, the guy who's kind of smart in this setting, and I'm sorry, its work is perhaps less appreciated than it should be, is Bloch, who observed that. So if you remember, I'm just trying to finish showing you that these are connections. I was talking about the same thing all the time, including stuff that I didn't mention, but you mentioned a lot, other people talked about it. So it turns out that if you remember, we had this Euler characteristic and the curvature functions of Bloch, and that was very useful to us. But there is a natural way of building or prescribing Ricci curvature to a graph or to a network or to a hypernetwork without doing anything artificial. And that's it, to look at it as a poset. So that's the name of the game, and you saw I'm not the first one who mentions that term here. Yes, I did a lot of posets. Yes, I just didn't, it didn't fit rightly into the flow of my ideas, but that's the way of doing it. So you can look at a hyper network, or more restrictively, from my viewpoint, at a hypergraph, and then on it, you have a natural way of defining the Forman, the discrete curvatures. So you also build, by doing this approach based on Bloch, you build your higher dimensional objects, and it comes ready with the curvatures and with Euler characteristic and everything. So we used it a bit, just trying to show you that it works. It's not, huh? Okay, so this paper, I didn't know. I found it online. I don't know where my papers are, okay? So this paper, full screen, how do I do full screen? Control L, oh yes. So Control L, so we have this paper, okay. Zoom in, how do I do zoom in now? I don't know. Sorry, more. It doesn't really matter. I'm just, can you see it at large, so to say? So this is a natural way of doing it. It's not, so those of you who want to do posets, that's how you can do it. And you see, you add automatically. You use a Hesse diagram. We heard that name here also. So in the end, I'm converging or unifying my presentation with the other presentations. So that's why I'm showing it, not because I'm especially proud of this or something, yes? So you have the formulas that you saw before. And I really don't know how to make things bigger here, but
Shouldn't be something of Zoom, no? So that's the.
yes, but where?
No, it should be. No? I should go. That,
Yes, perhaps here.
that should be here.
View.
View,
Where? Edit? No, view.
and this control plus, okay, yeah. Try
Okay.
control plus. Where is
Plus.
the plus?
Where is the plus?
Where is the plus?
Good
Here,
question.
here.
There is a plus, control plus. Okay. Nope. Does nothing. I don't know. Let it. Yeah. Oh, okay. Excellent.
Yeah.
Beautiful. Thank you so much. I mean, I don't know why when I am faced with the computer in this standing position, facing a public, I'm a total idiot, yes? But don't tell that anyone else. You officially, I'm an idiot, yes. Sorry. It's okay like that. Leave it. Yes? Okay. It's much better? Yes, it's better. So we have experiments. That's what I'm trying to say. So by thinking of these objects as posets in a natural manner, looking at their Hesse diagrams, you build them as hyper objects, and they have natural curvature, Forman curvature. Therefore, you can do persistent homology with Ricci curvature or with Banchoff, whatever you prefer. So that's what I try to say. And I'm not just trying to show that you might have thought that I did something different from others, but well, no. It's not that I did really something different. Just I painted things with a curvature taste. And so this, everybody has an own tool, and you have a big hammer, and everything looks like a nail. And my hammer is called curvature. That's all. I think I'll stop here. Okay, it's. Do you? If I have more slides if you want, but I think it's better to desist right now. Okay, thank you so much.